introductory lecture by Professor Dineshkumar Harursampath. I think most of you who have joined here already know Sir and know Professor Harursampath. You have been with him, worked with him, many of you, and I think whoever is new, it's very hard to kind of, let's say, introduce Professor. I'll just put it in a very couple of words here, and I would just say that he's a faculty at IISc in Aerospace Engineering, and he has been inspiration to a lot of students, and he has a huge academic family, and nearly more than 100 students and postdocs, PhDs, master students, and research assistants, and so on. I think if going by his bio, that is what he says would be his most significant contribution, right? But we have all been inspired by him, and the number of people who are here for this lecture speaks to itself about Professor Harursampath. And without keeping everyone at bay, I would probably give the screen to Professor to go ahead with the presentation and with the talks. Thank you very much, Professor, for joining us today and being gracious enough to talk to us. And it is very nice to have you here. And I'm looking forward to your presentation and talk.
Thank you very much, Ajay, for that kind introduction. First of all, I'd like to start by heartily congratulating you on beginning this forum, the mechanics discussions. I think it's a much needed one at this stage. And the aim that you have, as you have put up on the LinkedIn pages and the other publicity material, is to discuss best and cutting edge developments in mechanics. And hopefully this talk will address some of those things. The title of the talk, as most of you would have already seen from the publicity material, is Inspirations and Equations from VAM, which is Variational Asymptotic Method, as many of you might know, for mechanics of student life. And so the title deserves a little bit of explanation. So I've just separated out the non-important connecting words like and, from, for, of, and focusing on the other 5: inspirations, equations, VAM, mechanics, and student life over here. Now, any kind of learning requires 3 levels. And these 3 levels are what the first 3 represent: inspirations, equations, and VAM. In ancient Indian way of thinking and way of learning, there's said to be 3 stages, that is Shravana, Manana, and Nitidhyasana. Shravana means hearing, literally, but it could also mean basically taking inputs either from talks, sounds, or by reading, which could be through a course, a formal course, an informal self-study, whatever. But whatever you do by hearing or reading or self-studying is at the most an inspiration. It doesn't take you much further than just getting inspired. So that first word, inspiration, actually comes from Shravana. The second one, equations, even for those of us who may not understand very complicated equations, basically it has an equal sign and something on the left hand side and something on the right hand side. And you go back and forth between left hand side and right hand side. And this is manana, or reflection, where you're trying to go between certain quantities on the left hand side and the right hand side, some of which might be known, some of which might be unknown, and you try to determine how to find those unknown quantities which may be of interest to you. So equations basically refer to that aspect of manana. And then, even then, it's not sufficient. If you have just got your inspiration, got your equations, you have to have a methodology to solve that and to utilize those results. And that's what Nitidhyasana is, and that's where variational asymptotic method comes in. The VAM portion is basically Nitidhyasana, where after hearing and reflecting, you're now trying to incorporate those things. And that's not only a science, but an art as well, the variational asymptotic method, a heuristic method, where you basically try to implement what you have been inspired by and what equations you have tried to solve into actual application. So that covers the learning aspect. Now coming to the last two important phrases or words in the title, mechanics of student life. Mechanics is studying anything which is in motion, and the most beautiful motion is that of dance. But anything else on this universe basically moves, and studying those motions is mechanics. And statics is a very special case of that dynamic motion, and therefore statics also forms a part of mechanics. Now here we're talking of mechanics of student life, and when I say student, I don't mean anybody who is particularly registered in a course, a formal course, but all of us are students right from our birth to death. If we stop learning, we are like dead men or dead women walking. So learning is a process which happens throughout life, and that's what a student really is. And it's that student life that we want to apply this to. But in the advertisement, you would also have seen a tagline that this talk is going to be about composite structures, in particular as applied to aerospace engineering. So that aspect will be brought in as well to show that that need not be considered as something separate from student life, and how the merger between these two takes place in the mechanics. I belong to the NMCAD Lab, which is a nonlinear multifunctional composites and analysis and design lab, and it's part of the Department of Aerospace Engineering in the Indian Institute of Science. So let's go ahead. So first half of the talk title is about inspirations and equations from VAM. So in this slide, I'll cover just the V part of the VAM, that is the variational aspect of VAM, to see what is the role of variational principles in mechanics and that is in general, and mechanics of student life in particular. So first of all, talking about the first word, inspirations. Inspirations always come from physics, whereas equations, the second word, comes from mathematics. Now physics, what do we mean by physics? The word itself comes from that which is physical, and which in turn means that which has boundaries. So anything which is having boundaries is physical. If it is boundless, it's no longer physical and is called metaphysical. So everything in nature you can see has boundaries. Boundaries in space, boundaries in time. So birth and death are the boundaries in time, whereas the physical boundaries that you see of a body, for example, are basically the boundaries in space. So inspirations always come from these. So it's basically nature inspired. Secondly, we talk about the equations from mathematics. They are derived, especially in mechanics, using two alternate approaches. And this is true for most other aspects of science as well. Science as we know it today, that is the Western science. So when you talk of mechanics, for example, you could derive those equations which you want to solve for the unknowns in terms of the knowns, either through the Newton's laws or through variational principles. Now Newton's laws, or Newtonian mechanics as we see, is a law, whereas variational principles are principles. Now there's a huge difference between a law and a principle, which we take for granted in most of our... Did I hear something? Okay, so which we take for granted during our undergraduate studies, but laws are typically like commandments, whereas principles are something which is a governing aspect which helps us to resolve things all by ourselves without being told do this or don't do this. So laws are more about do's and don'ts, whereas the principles are the governing factors based on which we ourselves determine what to do and what not to do individually. So Newton's laws are based on vectors, which means they have not only a magnitude but a direction as well. On the other hand, variational principles are based on scalars, for example, energy, which do not have any direction as such, they have only magnitude. So it's basically a single quantity which forms a part of a functional and which is very similar to an Advaitic approach or a non-dual approach. Whereas the vector is having two aspects to it, the magnitude and the direction, and therefore it's a Dvaitic approach. Now, Newtonian laws involve differentiation, whereas variational principles involve integration. So again, there's a huge difference over there. And Newton's laws are the law of karma. For example, the third law says every action has an equal and opposite reaction. On the other hand, the variational principles are a game of Leela. Now the question is, how do you go from a law of karma to a game of Leela, and is it all necessary to do that? So that's what mechanics is all about, going from Newtonian mechanics to Lagrangian or Hamiltonian mechanics, and that's what we will see now. So it's much more fun playing a game rather than just following the laws. So that's the idea of going to variational principles. But the advantages don't end there. There are lots of problems which can be solved only by using variational principles. Newtonian laws will not be effective over there. And these are non-trivial problems involving non-linearity, etc. And we will see why as well as we go along. Now, before we go further, we should understand that there are various components to the variational principle. I've listed 6 here, which are the most important ones. You have a functional, some constraints, dependent variables, independent variables. The dependent variables are defined within a certain domain of plausible or feasible or admissible functions, which we call as the fields of operation. And then, of course, once you have this problem defined in this way, we go for a solution process, which typically involves the calculus of variations. Now, the functional is a single quantity, as I said, in the variational principle, basically being an Advaitic approach. So the objective here is to identify a particular quantity which you want to either maximize or minimize. And these two together, if we don't know which to do, in many cases, wonderfully, it still works. And we call it a stationary principle instead of a maximum principle or a minimum principle. Now, let's take the case of the student life. So here, you would want to maximize the inner state of pleasantness, what we call as Ananda. So Ananda becomes the functional over here. Secondly, if you look at constraints, the constraints can come from both within the system as well as from outside the system. When they come from outside the system, we call them environmental, which is basically the boundary conditions. And then you could have certain things which are coming from within the system, which could be physical and emotional, or in a mechanical system, the emotional aspect is basically related to the controls aspects, the sensors and actuators and how they communicate with each other, how the feedback is done. So a much more refined way of putting this is in terms of vignas. So constraints are like vignas or obstacles, and these are of 3 types. The environmental ones, which are called as Prakriti Vigna. Then you have the physical obstacles, which could be the loading in a mechanical situation, for example, the Sthula Vignas, and those which are much more subtler, which are the Sukshma Vignas. In the case of student life, it could be emotional obstacles. In the case of a mechanical system, it could be obstacles coming from the control characteristics. Next, we have the dependent variables. Now, the dependent variables are basically things that you have to determine which of those particular options for the dependent variables will maximize or minimize your functional. So those dependent variables in the case of a mechanical system would be, for example, displacement variables. Now, in the case of student life, it's the very way of life. In other words, what path are you following? Whether it's Karma Yoga, Bhakti Yoga, Jnana Yoga, Raja Yoga, or combinations of these called the Sankhya Yoga. So now, these dependent variables cannot be chosen arbitrarily. They have to be chosen within a certain range of what is allowed. And that's where the fields of operation or domains come in. So the domains of operation basically limit your choices or options for the dependent variables. Which range of dependent variables can you actually search for the optimal from? So in the case of Karma Yoga, you search what all can you do with your body, which includes, of course, all the sensors and actuators, the 5 sense organs and the 5 actuating organs. With respect to a path like Bhakti Yoga, you cannot go beyond your mind. It has to be within the realms of your mind. So again, you set up a subset of options in which you search. When it's Jnana Yoga, you search within your intellect, and when it's Raja Yoga, you search within your energy bodies. Now, this whole thing, the body, mind, intellect, and energy, are basically what is a robotic domain. And within this robotic domain, you have to search for solutions. It might sound very limiting, but actually it's a huge set of options that you have, and selecting the right option for you at that particular point of time, which could be different at a different point of time in life, is what the functional optimization is all about and variational principle is all about. Now, these dependent variables are not necessarily things which when solved will be constants. They can be functions themselves. And what are they the functions of? The functional, first of all, is a function of the dependent variables. Now the dependent variables in turn are a function of the independent variables. So whether it's a mechanical system or it's the human life, in both cases, the independent variables usually are space and time. And very interestingly, this 4-dimensional space of 3 dimensions, x1, x2, and x3 of space, and t, which is the time, is basically called by a single word in our scriptures, which is kala. So kala most people understand as just time, but very frequently in the Vedas it's used for space as well. So it unifies the set of independent variables, and it's measured through the sensors to actuate the dependent variables, which we just saw. Now coming to the solution process, as I said, it's mostly calculus of variations today, but we will soon see the history behind it. Before calculus of variations, variational principles were tried to be solved by using just calculus, and even prior to that by just using geometry. But when you're using calculus of variations, all that you're trying to do is to identify the dependent variables to maximize or minimize the functional, basically a stationary value of the functional, through optimal conflict resolution, which means taking care of the constraints. So in the case of human life, it just translates to identifying the right combination of karma, bhakti, jnana, and raja yoga to maximize the ananda or bliss through optimal conflict resolution. And these conflicts are both external conflicts as well as internal conflicts, as we already saw in the second aspect, which is the constraints. Now let's turn our vision towards classical mechanics and the role of variational principles there. First of all, we should understand what is the domain of operation of classical mechanics as opposed to mechanics in general. So now this depends upon the sizes and speeds that are involved in the study of a particular system. The speed can be either of the order of the speed of light, or it can be much lesser than the order of the speed of light, which we represent by c in the first row of this particular table that you see over here. As far as the sizes are concerned, they can be all the way from atomic or subatomic sizes going up to molecular or a little more than the molecular sizes, and then what we actually see with our naked eyes, which can run all the way from millimeters to kilometers or more in the case of celestial mechanics, for example. Now, what color code I have used here is basically red for what I'm not covering in this particular talk, and the green or dark green that you see over here is basically for things that will be covered over here. So for lower speeds and larger sizes, we have a certain branch which we call as classical mechanics, which can be Newtonian, Lagrangian, Hamiltonian, etc. Now, that in turn, the classical mechanics is divided into two parts: the micromechanics, which is at a lower length scale, relatively much lower length scale compared to the macromechanics, which is something that we can see with the naked eye. Now, there's a lot of information transfer happening between micromechanics and macromechanics, because if we understand the micromechanical theories, we can set up the macromechanical theory in a much more effective way. But an even better and more refined possibility is to transfer information back from micromechanics to micromechanics, what we call as multi-scale modeling, in order to have much more information as to how to build up the structure. So this is the domain of this particular talk. We will not cover very high speeds at large scales of matter, which is relativistic mechanics, or at smaller scales of matter, which is quantum field theory, QFT, or neither will we at lower speeds cover very small dimensions, which is in the realm of quantum mechanics. But a lot of things that we talk about can, with appropriate modifications, be extended to these as well. Now let's look at the variational principles history. As I told you, though today we are talking of calculus of variations, it was not always that. It used to be calculus earlier and geometry even before that. First of all, people wanted to understand reflection. For example, a reflection from a mirror, you see that, you remember from your high school physics, that the angle of incidence is equal to the angle of reflection. Why is this? There is a variational principle governing that, and that's where it all started. The variational principles started from the fact that people wanted to understand why angle of incidence is equal to the angle of reflection. And they ended up finding out that it is the least distance between any 2 points. If you take any 2 points, A and B, and you have a mirror in front of them, for the light to move from A to B via the mirror, it has to always take the path which is of least distance. And if you find out that, it will show you purely from geometry, no need of calculus, leave alone calculus of variation. It will show you that it is the least distance. So that's the seed for variational principles. Then the sprout for variational principles was people then wanted to understand the next aspect of optics, which is refraction. So there geometry failed, because if you try to find out the least distance, it's not what happens. Light bends when it goes from one medium to another medium. And why does it bend? If it bends, then obviously in moving from point A to point B, it is not taking the shortest path. Instead, it is taking the shortest time to travel from point A to point B, and that's why it has to bend. And why is that in turn? Because the speeds of light are different in the two different media. Now, for refraction to be understood and seen, why Snell's law is valid, that is basically the ratio of the sine of the angle of incidence to the angle of refraction. Let's say if you have two media, 1 and 2, and the angles in them are alpha 1 and alpha 2, then sine alpha 1 by sine alpha 2 is equal to C1 by C2, which is basically the ratio of the speeds of light in those two media. And this Snell's law is basically something that you get when you minimize the time required to go from point A to point B, from where point A is in one media and point B is in the second media. Now, this is all in optics. Now, if you want to go to mechanics, even calculus is not enough. Geometry and calculus are not sufficient. You need to go to the calculus of variation. And calculus of variation differs from calculus, as many of you might already know, in the fact that we deal with functionals instead of functions. Functionals, for the very beginners, we can call it as functions of functions. And that's the complication that mechanics brings in. So as I said, variational principle was first introduced for refractive optics, and again it was introduced in two different ways, both variational principles. One by Fermat, who did it by using the least duration of time taken to travel from point A to point B, which is the right way to do it. But Leibniz, a great person himself, a great scientist as well, used a wrong quantity to optimize, a wrong functional, which is basically the resistance of the media to light multiplied by the duration, which is basically nothing but an impulse. And he minimized that. Both of them ended up with the same result. But one was based on a correct assumption, the other was based on a wrong assumption. And what was the wrong assumption here? That light travels faster in a denser media compared to that in a rarer media. Would you believe that? Faster in a denser media. And the argument for that was that he was observing rivers, and when a river narrowed down, it flew faster. So when there were more obstacles, it flows faster. So he felt the same thing about light, that it would go faster in a denser media like water compared to air. That was not the case, but still he ended up with the right result. So assumptions and the rightness or wrongness of that is very, very critical, because that's the foundation on which you're building up your theory. You may end up with the right theory by accident, but not consciously. And that's the problem with wrong assumptions, and we will revisit that soon. So the same solution, but Leibniz through same wrong assumption as Descartes. Now Descartes didn't use variational principles. He used Newtonian kind of mechanics. It's a vectorial approach, which means that, as I said, once again, like the wrong assumption of Leibniz, even Descartes had assumed light travels faster in a tensor media. Now let's move on to mechanics. And here, the first contribution of variational principle in a very, very simplistic way, not the way we know it today, was by Bernoulli. And when we say Bernoulli, you have to be very careful in defining which Bernoulli. This is Johann Bernoulli, not Jacob Bernoulli that you know of, or any of the other 6 stars of the Bernoulli family. It's more like a Vyasapita, where everybody is called a Bernoulli there. And when we say Bernoulli's law or Bernoulli's principle, etc., we think it's the same person. No, there are many people who are involved over there. Now, Johann Bernoulli, very interestingly, was the guru or teacher of Euler. And Bernoulli's least duration for any body's movement through a frictional groove under self-weight between two given points on a vertical plane. So if you have a vertical plane and those 2 points are also in a vertical line, then it's obvious that it's just going through a straight line. But if those 2 points on the vertical plane are A and B, not in a vertical line, but on the same vertical plane, then you basically look at how this ball would travel through a groove and which groove would it choose if it had options. And that's basically the problem which was solved using the variational principle, and the solution turned out to be not a straight line but a cycloid. If it was shortest distance, it would have been basically the straight line, but the objective function, or the functional in this case, had to be the duration. So the whole purpose of introducing this history is to have these takeaways. You will see most of the yellow highlighted things that I have on my slides are the takeaways from this. So the takeaway from this discussion on the top of the slide is that there are lots to learn from other fields, in this case optics, and lots to teach others too from mechanics. So this open-mindedness to learn from other fields is very, very critical. Mechanics itself is a big ocean, but we should not limit ourselves to mechanics, and we have to look at other aspects of science, in particular physics, to see how we can learn from methodologies and processes over there to see how we can do better in mechanics with lesser number of assumptions and still reach the right solutions which are useful in applications. So being governed by physicality is very, very critical. So next, let's look at classical mechanics. Newtonian, as I said, to Lagrangian to eventually Hamiltonian, which is what most of us use today, especially if you're using finite element analysis software. With or without our knowledge, we're actually employing Hamiltonian principles over there. Newtonian is applicable where you have no interactions between multiple fields. For example, the mechanical forces and electromagnetic forces, for example, or if there are very simple field interactions. Once there are more complicated field interactions, Newtonian mechanics fails. You have to go for variational principles, and there are tons of variational principles. One common one is the Lagrangian approach, and then which was further refined by Hamilton, it's called the Hamiltonian, and which is the only way out for physically sensible, nonlinear, higher derivatives and kinematical constraints involved problems. So either you have constraints which are kinematical in nature, by which we mean, for example, joints. So you could have a revolute joint, for example. There are certain constraints which are associated with it. Higher derivatives are involved in the problem formulation. Then again, Newtonian mechanics fails. You know that the second law of Newton, force is equal to mass into acceleration, involves a second derivative of the displacement with respect to time. When something more than that is involved, then again Newtonian mechanics fails. And then you should have a physically sensible situation. If you have, then it's usually nonlinear, and therefore once again Newtonian mechanics fails. You have to go for a Hamiltonian approach. Now the motion of macroscopic bodies is basically from a deterministic present, which basically gives you the initial conditions, and soon to the next update that you have in the next time step, which is basically a stochastic future. So basically a prediction is involved from the deterministic model to the stochastic model, and that's basically what the motion always means. And even in statics, you're basically talking of equilibrium positions or their stability. So you're basically talking of disturbances, etc. So you're talking of moving from one equilibrium position to another. So motion is actually involved, just that the time scales are much shorter over there. Now the motion of macroscopic bodies being understood, the takeaway from this is that the present moment and environment are inevitable. You can't cry about your constraints in a mechanical problem definition. Same way with life. So the present moment and the environment have to be accepted as they are. They become the initial conditions and boundary conditions of the problem that we are trying to solve. And the present moment becomes an initial condition, while the present environment becomes the boundary condition. So this moment is inevitable, but the future is completely tailorable, and that basically depends upon the governing equations. So next we talk about how these variational principles and classical mechanics go forward to understand system design, because most of us as engineers are involved with system design, and in life too we are talking about life, or this whole what we are as a system. So then it depends on certain parameters, as we say, the dependent variables. And how do you choose them is the question. How do you solve for them? Now the ability to respond as needed becomes the critical thing. That's basically where smart structures or adaptive structures come in. The whole idea of smart or adaptive structures is that now you have an ability to sense what the environment is, and based on the sensor we supply a feedback to the actuators to actuate in such a way that you're now changing your basic system characteristics in order to cater to the new environment, the changed environment. And that takeaway for us in life is responsibility. And very interestingly, this word responsibility, the root word is ability to respond. The root phrase is ability to respond. And that responsibility is important in student life. That's basically where you design your system, you change your own characteristics, whether it's at the body level, mind level, or the emotion level, which is the intellect, or the energy levels too. You try to modify them according to the needs of the situation that you're encountering. Now the second half of the talk is about the mechanics of student life, the analogy of composite aircraft structures and student life. Now why composite structures because that's what most of nature is. If you look at wood in the case of plant life, or if you look at bones or skin in the case of animal life, they're all composites in the sense that they're made of more than one material at a macro level. And why aircraft? Because or aircraft, or for example any aerospace structure, that's the pinnacle of the constraints that you can have in terms of the requirements of the material, the geometry, and the structure as a whole. So you're talking of the highest levels that can be achieved and how we basically target them. And we want to compare composite structures with student life here. And these are based on historical facts from Western science. If you look at the parameters involved, is the same set of parameters that we talked about, just that I've listed the boundary conditions and initial conditions here separately. So along with the governing equations, which need not always be differential equations, they could be sometimes algebraic equations, sometimes integral equations, sometimes integral differential equations, or combinations with algebraic equations, whatever. But this is basically a system that you're trying to solve. Now, the objective functional, as we understand Hamiltonian mechanics today, is to minimize the integral of the Lagrangian, which is the difference between the kinetic energy and the potential energy. And this in turn is basically written over here between the time instance of consideration, that is basically the duration that we are interested in from t0 to t1 times. We want to see how this Lagrangian's integration over time can be minimized or stationary in general. Now, if you look at the student life, the kinetic energy is nothing but life energy, whereas the potential energy is something that you have inside, but you're not utilizing it. That's basically death energy. So life energy and death energy. Life and death are two sides of the same coin. You cannot separate them. You cannot see them separately. And it's this difference between life energy and death energy. How much more is the life energy compared to the death energy, which is what determines your inner state of pleasantness. So whereas we might be minimizing the Lagrangian over here, we would be maximizing the difference between life energy and death energy over here, the inner state of pleasantness, which we call as the Kundalini Shakti. Next, let's talk about the constraints. In the case of composite structures, especially when applied to aircrafts, the support and loading conditions and the minimization of the weight become very, very critical. Now, in the case of life energy, before that I would like to mention that Leibniz, this is not something which is peculiar to our system of Sanatana Dharma as well. Much more recently, that's about 400 years back, that is, compared to the thousands of years over here, Leibniz said that kinetic energy is a living force. Of course, energy and force are not similar quantities, but he's talking about it in a metaphysical sense, that whereas kinetic energy is a living force, pressure, which basically causes the work potential, etc., the stresses in general, are dead force. So this is something that even Western scientists of the repute of Leibniz have recognized, that there is something what we call in our systems as life energy and death energy as the living force and the dead force, kinetic and pressure. For some motions, action is minimum. That is the action functional that we will talk about shortly. And for others, it is maximum. So this is again very interesting, because here we see we want to maximize Ananda and here we want to minimize, but in both can be generalized into one word, stationary, because stationary means either maxima or minima. So in that sense, again, Leibniz is not a person who stands out in this. Euler and Kraft had a lot of discussions. In one of those letter communication, Kraft says to Euler, this is again about 250 years back, he says, and I'm rephrasing it, it's not exact quote, thrifty Mother Nature. That means Mother Nature is very, very efficient. She doesn't spend unnecessarily most of the time. Thrifty Mother Nature manages with least possible resources, if she can do it, and which is most of the times. But if not, she pays honestly and as much as possible, not to be reputed a miser. And the example that I can give is in the case of evolution, where we are trying to manage with least possible. That's what nature does. That's why you see evolution as a very, very slow process, but very efficient. On the other hand, a natural disaster like a tsunami or the COVID-19 pandemic that we are facing today, these are situations where nature pays huge amounts. So here there's a maximization involved. So whereas in evolution a minimization is involved, in a pandemic or a natural disaster a maximization is involved, but both are stationary. So that's the bottom line, stationary, and that's where variational principles make so much of a difference. Now coming to the constraints, the support and the loading conditions. Did I hear something? Can everybody please mute their microphones? So the constraints, as I said, are the support and loading conditions. And here again, a very important takeaway from a Russian scientist, Mosolov. He says one needs to feel the constraints. Feeling the constraints is very important. So these constraints, as I said, can come from both within the system and from outside the system, whether it's a mechanical system or a human life. And you need to feel for these constraints even when you're designing a mechanical system. You need to feel how a cantilever beam is supported at one particular end. You have to feel it yourself. How a cantilever beam is having a distributed load. It could be the wings of an aircraft with a lift distribution, a drag distribution. You have to feel that. Do not separate your derivations of mechanics from life. They are absolutely related, and only when you see this parallel, you would be able to make immense contributions towards the understanding as well as the further developments, what Ajay calls the cutting edge developments or the real benefits. So these constraints, as we saw in the case of student life, are environmental, physical, and emotional. Now the dependent variables are displacement field or generalized coordinates, Q, which basically the number of them determines the degrees of freedom, and in a continuous system they become infinite. So that's where functionals come into play. So here in the student life, the dependent variables are the path to take using our actuators. Next, the independent variables, as I said, are spatial and temporal, xi and t, whereas they are space and time sensed using sensors in the case of the student life. Now the governing equations are determined by minimizing the integral of this Lagrangian that is basically over here with respect to the q's, which are the generalized coordinates. So those Euler-Lagrange equations, most situations are differential equations. Whereas here, in the case of life, these governing equations are continually evolving. They are dynamic set of equations. They are not the same equations you had yesterday as you have today. Because your emotions, thoughts, words, deeds, these are all characteristics of the system in operation, and they change the very governing equations based on the choices and decisions made out of free will. Next, we talk of these two conditions, the boundary conditions and the initial conditions. Boundary conditions in the case of a mechanical system are the support and loading conditions, whereas in the case of student life, they are the current generic transit chart at the location of the individual. The initial conditions are the undeformed configuration or plastic deformation if you have. Then you have to take into account the time history of what this particular structure has gone through before you arrive at the initial configuration, therefore the initial condition. In the case of the human life, it's the birth chart or Jataka or horoscope, but no, every moment becomes an initial condition because you have changed things right from your birth to now, and that's where the plastic deformation analogy comes in. So no longer you depend on the birth chart. Now what is the situation that you're in? How have you changed from your birth to now? And that becomes your initial condition, and your governing equations are used to see how your future can go forward in the best possible way. And that's the optimization or variational principle involved over here. Now let's put everything in a nutshell over here. The mechanics over the ages, not talking about our culture in India or the East, but mostly in the West, a much more recent history. But even there, you see Aristotle approximately 2,400 years ago. And this is not his own discovery. He is basing this on his predecessors, which means this is much more than 2 millennia ago. What he says in one of his profound works, almost like a Bible for the mechanics community, is that all manifestations of nature, again I'm paraphrasing, this is not an exact quote, all manifestations of nature follow easiest path that requires least effort. I have highlighted through bold and underline the words easiest and least effort because very, very unfortunately, in spite of this ancient knowledge, not only in the East, but also in the West through Aristotle and his predecessors, we have been talking this nonsense that there isn't a substitute to hard work. Everybody talks hard work, hard work, hard work, right from parents to teachers. No, hard work is true only for stupid donkeys who do not love their work. Once you love your work, you will do it in the most efficient fashion. You never need to do hard work. You will do it most effectively and most quickly. We saw the examples in the previous problem in nature where light takes the shortest distance in reflection and the shortest time in the case of refraction. The same in the case of the cycloid, the shortest duration from point A to point B on the vertical plane. So whatever we need to do it efficiently so that we conserve on the energies, conserve on the time. That leaves us much more energy and time to do other things. So hard work is not something that we should promote as a great quality. It is efficient work that is much more of importance. 100 years later, Archimedes knew already the laws of statics, which is a special case of dynamics. So 19 centuries later, that is just about 400 years ago, a huge bunch of scientists came up. Galileo, Descartes, Fermat, Newton, Leibniz, Bernoulli, just to name a few. And Galileo's two principles formed the basis of Newtonian mechanics. And this was in the spirit of Euclidean geometry. But these two principles are just mind games because experimental validation is not possible there. And what are those two principles? One, that the laws of mechanics are invariant with respect to inertial frame changes. But the fallacy is that there's no such thing as an inertial frame. It's impossible. But for all practical purposes, we assume that the accelerations are of no consequence of a particular frame, and we treat those frames as inertial, and we get along. And very well for all that we are today. The second principle of Galileo, which again forms the basis of Newtonian mechanics, is the inertia principle. The inertia principle says that non-interacting body's motion remains uniform. So in other words, if a body is isolated, it will remain in a state of rest if it is already in a state of rest, or if it's moving, it will move uniformly the way it was moving. This is Newton's first law, but it was derived from Galileo's second principle. And this happens in an unbounded space and in the absence of interactions. What is the fallacy here? There's no such thing as an isolated body. We are all inclusive. Everything interacts with each other. How strong is the interaction is the only question. So leave alone unbounded space. How do we know that space is unbounded? We just assuming that space is unbounded. But physics or physicality is all about boundaries. Then 100 years later, about 300 years ago that is, the first variational principle in mechanics was given by a person we unfortunately even those of us working in mechanics don't hardly hear. That is Maupertuis. Maupertuis as the first person who introduced this concept of the product of mass, speed and distance. Very funny quantity. Nobody knew physically what it meant. And later on people started calling it action. So he said that we have to minimize action. But later on it was showed that this action is nothing but the kinetic energy with a factor of 2 here and there. So this was followed by Lagrange and Hamiltonian to a much more refined mechanics or variational principles for mechanics that we know of today. So basically there are lots of variational principles, not only the Hamiltonian that we mostly use, but they are all bounded by a common definition. A variational principle is just an assertion that some quantity which is defined for all feasible or admissible process, not any process whatsoever. There's a certain range in which you have to search for your solution. And that reaches that particular real solution, that choice amongst the admissible process reaches a stationary value, could be maxima or minima for real processes, yielding governing equations for real processes, possessing a special structure. And this special structure again is one of the huge advantages of using variational principles as opposed to Newtonian mechanics. And again, we lost another 260 years approximately before 40 years ago, the variational asymptotic method was introduced by Professor Victor L. Berdichevsky, where he communicates the principle behind that, which is far more important than its actual application, that the most fundamental law of nature revealed up to now is the reciprocity of physical interactions. The more than one body or more than one system or more than one field, and one field operates on the other field operates on this, and there is a reciprocity involved, and this reciprocity comes out directly whenever you use any variational principle. And that's the advantage of using variational principle. Once again, the takeaway here is that it is the law of karma. Every action has an equal and opposite reaction. Now, all of microphysics or micromechanics in our case, these equations possess such a structure where there is a reciprocity of the field interaction, be it the displacement field and the loading field or anything else that you might be dealing with. Now, this micromechanics is what helps us develop the macromechanics. And macrophysics operates therefore with averaged out characteristics. Because microphysics has so much of heterogeneity, you want to go for an equivalent homogeneous structure, you go about averaging this out, and those average characteristics of microfields in the case of equilibrium processes leads to another field called thermodynamics. Most people think of thermodynamics as a separate subject from mechanics. No. Mechanics of microstructures is what leads to one part or the most studied part of thermodynamics, namely the equilibrium thermodynamics. So how much time do I have, or I've already overshot?
No, sir, you can please go ahead.
Okay.
I think everybody is quite interested in what you're
saying. Thank you so much. So just like Man Ki Baat, which is starting now, this is Mechanics Ki Baat, and let's continue on our path. We talked about the history in the previous slide, all the way from before 2,400 years to before 40 years. So now, why we researchers continue to look at newer and newer models? One is the fact that the old models have a problem, have a limitation. What is that? They are of insufficient accuracy or insufficient speed or both. Being inaccurate in itself is bad, and being slow makes it worse. Inaccuracy is like rajas and slowness is like tamas. So why can't we move towards sattva is the whole idea of new models here. So the need to change or shuffle across old models is what most people are doing. They take the model of Tom, Dick and Harry and combine it in some way and come out with a publication, just like a publishing machine. So even for minor changes, we have to keep on coming with combinations of the older models. No, not necessary. Some new models can be much, much more robust if they use the variational asymptotic method. Next, as I said, assumptions play a very critical role, and most people working on mechanics, unfortunately, some big names too, are using either invalid assumptions or ad hoc assumptions valid for only specific situations, or both. And therefore, we need to move to new models. Next, we have an empirical nature of some old models, so you have to keep on correcting them. A classic example is Timoshenko's theory for beams, or for that matter thick shells, where you need a shear correction factor which depends on the geometry. So basically this is nothing but curve fitting, tweaking. Timoshenko is a great person. He has made huge contributions. Nothing to belittle that, but we can be better. We can be much, much better than that, because we don't need such empirical things. We can do it in an analytical fashion, or at the most semi-analytical. Next reason why new models. Non-classical and non-linear phenomena are observed in reality, but they're not captured by the old models. So then what good are those old models for those situations? So you need new models. Next, low reliability of the old models. In other words, the old models are not something which we will use for detailed design. You might use them for preliminary design just to get rough approximations, but once you want to do it, especially a design of an aerospace structure, no way. Next, therefore, the goal is to illustrate this potential of the new models developed through the variational asymptotic method. So I'll be talking of a sampling of worldwide advances in modeling techniques, illustration of detailed studies both at my alma mater, Georgia Tech, and where I currently work, the Nonlinear Multifunctional Composites Analysis and Design Lab at IISc. So the emerging techniques to model composite structures, the vision here is to enable getting as close to the truth, which is basically the model mimicking reality as closely as possible. Remember, the model can never become reality. Model is always a model, even if you use the most sophisticated tool like the variational asymptotic method. But how close do you want to get to the truth, and can you really get there? That's what we want to enable through our vision. And this is valid both for life as well as the equations and solutions that we develop. Now again, you get as close as you intend. So the intention of the user is important. But the most important thing here is that just like nature, we do not want to do hard work. It has to be efficient work. So with least effort, we want to get as close to truth as we want. So with this kind of a vision, what is the mission that is involved? It's to better understand the relevant phenomena happening in nature, in reality, in aircraft structures, aerospace structures, or in life. And those are not classical at all, which means you need at the same time both high fidelity and high efficiency. Usually these are at loggerheads. If you have something which is high fidelity, it's usually something which takes a lot of time and so inefficient. If something is very efficient, maybe you can do it using a calculator or even just derive it on a piece of paper, back of a tissue maybe, but it will not be accurate. Now how do you go to the golden mean between these two? That's where our mission comes in, which means we need to have improved techniques, not only for analysis, but also for design, not only for current applications, which is important for the industry, of course, but for futuristic applications as well. That's where the academia sees its relevance. to work on problems for 10 or 20 years down the line, or even more in the case of science departments. So with this vision and mission, we need to have a strategy. It's not sufficient to have a good vision to see where we are heading and to have a mission of how to accomplish it, but you have to strategize and to have tactics to accomplish that strategy as well. So the strategy here in the case of the mechanics problems is to look at nonlinearities, because real life is nonlinear and there are different types of nonlinearities, some associated with the very geometry of the system and the very geometry of the system, how it changes with the application of loads or in different environments. And then the material as well, what we are made out of, the system characteristics are nonlinear, and how those nonlinearities in our system, be it our body, mind, intellect, or an aircraft wing for that matter, how they change, how those material properties change, and change with age, for example, and how they interact in an evolutionary fashion. So now, if you want such a lofty vision, such a great mission, such an immense strategy, obviously you should have some enablers to do that. Otherwise, it's all great intentions, no capabilities, and a failure. So there, the state of the art that Ajay has in his tagline comes into picture. You have to have state-of-the-art mathematical approaches, because modeling is all about mathematics, taking the physics and using mathematics to come as close to it as possible. So you need state-of-the-art mathematical approaches. One we have already discussed briefly or pointed out, the variational asymptotic method. We'll talk about a little more detail later. Next, non-deterministic techniques. Most of classical mechanics, the way it has worked, is deterministic techniques. You know this fact at a particular point of time, you have to predict at a particular other point of time. This is no better than astrology. You know a particular initial condition, you try to predict the final condition. Whether that will really happen or not, there's so many uncertainties. And that's where stochastic models become very, very critical. So we need to use non-deterministic techniques if we want to mimic reality much more closely. Third tool that we have, enabler, is the concurrent multi-scale modeling. I briefly referred to this when I was talking about the need to go not only from micromechanics to macromechanics, but come back in order to understand damage, for example, and therefore design a structure which is much more less susceptible or not at all susceptible to damage in the typical loading scenarios. And finally, nonlinear domain decomposition. You don't need to apply a very complicated, complex theory to all aspects of you. Certain aspects require a very simple theory. So identifying which part of your domain of the problem, and domain I don't mean necessarily spatial domain or temporal domain, it can be way beyond that, a much more abstract domain, but you basically divide the domain into parts in an automatic, systematic way using rigorous mathematics, so that the domain gets decomposed and you know where to apply a much more high fidelity theory and where to apply a very simplistic theory and still get away with very good results. So with this, I will probably come to this particular slide, and then we'll probably stop because I probably am overshooting too much with the time. How are composites modeled? As I said, anything that is modeled, leave alone composites for aerospace structures, any modeling requires making assumptions. Now, are all these assumptions necessary? No. Are all these assumptions relevant? No. These are two different questions. Sometimes an assumption may be necessary but irrelevant, and sometimes an assumption might be relevant but unnecessary. We will see what those are in the case of a composite, especially when it's used for aerospace application. The first one typically made is that a composite, especially in relation to polymer matrix composite, but applies to metal matrix and ceramic matrix as well, is that it's an elastic material. For most of the deformation, when you have very less strains, this is valid. So you have an elastic material. So therefore, I'm putting this up in a green font. Next, something which may or may not work is material linearity. We say that the material behaves linearly. In other words, if you increase the stress by a certain factor, the strain increases by the same factor. If you double the stress, the strain gets doubled. So this is material linearity. It is valid in many situations, but not always. So that's why it's in a yellow font. Next, a green one. No body moment distribution. People have heard of body forces distributing within the structure, and they do take into account in deriving the 3D equilibrium equations valid within the structure, but they do not take the body moment distribution and end up with a wrong conclusion that shear stresses are complementary, tau ij is equal to tau ji. This need not be the case, especially with examples such as magnetic materials where you have a dipole moment distribution. These two shear stresses have to be different in order to get moment equilibrium. Next, another thing which is valid, but because we mostly don't use magnetic materials in many of our primary structures, it might still be valid. Therefore in green. The fourth assumption is that there is something called strain energy density which exists. And this is very critical in modeling any material or structures, especially in composites. And because of this, a lot of simplifications in the model happen. Now again, this is something which is valid in most situations for most materials that we deal with. Next, we say that the material composite is orthotropic. In other words, given the properties along three directions which are not collinear, we can find the properties along any other direction. And these three directions could, for example, be along three perpendicular directions, but not necessarily. Any three directions which are not parallel to each other, if you know the properties, you should be able to get the properties in any other arbitrary direction. That's orthotropy, and again valid for composites. Next, transverse isotropy. In other words, you're basically saying that in a particular plane, the properties are the same in any direction. And in the case of a composite, as you see in this particular picture, if you take just one layer in a plane which is perpendicular to the fiber direction, you see that the properties are similar to each other, in fact identical, and that's what transverse isotropy means. Again valid, therefore in green. Now coming to the danger, guys. First of all, a lot of people make this assumption of plane stress state. May be true accidentally, but those are for some specific cases. In many situations, plane stress doesn't work, especially if you have thicker structures where transverse shear becomes very critical. In many situations, there are pressure loadings because of which there is transverse normal stress as well, which again is not accounted for in a plane stress. And the most simplest situation where you have, let us say, Poisson's effect, again you see plane stress situations might lead to erroneous results. Next, there is a Kirchhoff law assumption which is made, this is in the case of plates or shells by two great scientists, Kirchhoff and Lau, that there is a linear distribution of the in-plane strains through the laminate thickness. That is, if you have a coordinate x3 along the thickness, the in-plane strains, which are the extensional strains, epsilon 1 along the one direction, epsilon 2 along the two direction, and epsilon 1 which is the shear within the plane. These are all linear in the x3 direction. That is, they vary in a straight line if you plot them versus x3. Same way you have in the case of the beam as well, but we'll not go to that right now. Again, a red flag for the displacement field which is assumed. Very, very common in the finite element analysis approach, where you assume a displacement field. Then how the hell do you expect to get results which are much more close to reality? Because it has to fit into what you have assumed. Some people who do not assume displacement field end up assuming stress field instead. Again, that's an unknown. Unknowns are to be determined. Give me a break. They are not to be assumed. Then the other problem, as we already discussed, empirical correction factors. So now, how to correct all of these is what the variational asymptotic method basically deals with. So for this first talk, probably I can end here unless Ajay feels that I still have time, because already I've taken a lot of your grace time.
Thank you, Professor. I think everybody is still quite interested, but maybe we can have another talk to also continue this.
Sure.
So I think probably a lot of people would have a lot of questions.
Yeah.
Even I have a lot of questions, but
okay.
probably open it up for our audience.
Absolutely.
I think Guru started out with a question.
I'll first stop sharing my screen.
Sure. Yeah. I think Guru already sent a question in there.
Yes, please go ahead.
Probably we can start with that, and I think anybody should be able to easily unmute themselves to ask a question. I think it should be okay there. Maybe Guru says, can we use the analogy of free will or a swaicha, the same as free energy limited only by imposed constraints in structure as in life?
Absolutely, Guru. I mean, your name is something which befits this particular question. Yes, free will is something which determines how our governing equations evolve. Because, as I said, you have nothing you can do about the current situation. The current situation is the way it is. This present moment is inevitable. To be in the present moment is something that is always advocated, but do you really have a choice? You have to be in the present moment. It is inevitable. And some people say, accept the present moment as it is. Again, do you have a choice? No, you have to accept it as it is. But you do have a choice whether you want to be in the present moment consciously or compulsively, accidentally. Whether you want to be accepting the present moment as it is joyously or grudgingly. Now, the choice you make to accept the present moment as it is consciously and joyously is what will determine your free will and therefore your free energy. So there's a lot of mathematical modeling that can be done with respect to this as well. And if you're interested, there's a collaboration right here. I'm proposing that. Thank you, Guru, for the question.
Thanks a lot for your insightful comments.
Thank you.
Yeah, so the floor is open for questions. Anybody else can feel free to join in and jump in and ask questions. Or I can also start pulling up people to ask questions also. So I see that Ramesh is there. Hey Ramesh, how are you?
Hi. Very great insight about variations and history of variation asymptotic method to the current state and future aspects. And it's always inspiration to listen Professor Dinesh's talk all the time.
Thank you very much, Ramesh. Do you have any questions or suggestions or comments?
Not exactly now.
Okay.
Maybe I'll come up early.
Sure, Ramesh. Thank you. Thank you for your feedback.
Yeah. So anyone else?
Sir, this is Hari Krishna. Very, very excited and happy to listen to your lecture. Really honored to listen to your lecture. One small doubt I have is this. You are mentioning that the potential energy is the dead energy.
Yeah.
But little bit can we modify the term? It is not the potential energy. Actually, first of all, before converting into the kinetic energy, there should be potential energy. Then only kinetic energy can exist.
Absolutely.
So maybe.
Absolutely. And that is the only reason why we call it death energy, because without death, you cannot have birth, and without birth, you cannot have death. These are two sides of the same coin. So life being considered without death is impossible. And that's why this transformation of energy that you very beautifully mentioned between kinetic energy and potential energy is so critical. And this is something that you see commonly both in the scientific community. It has been very frequently mentioned. I just brought out one such quote, but it's something which is very frequently mentioned, and much before that we've been doing this in our ancient scriptures as well. And potential is not something to be looked down upon. Potential, in fact, is something that is just like death, very phenomenal, and it's from that everything else arises. Very unfortunately, in the recent years we have been looking at death in a very negative connotation, and therefore the potential also gets seen in that particular blunt vision, so to speak, with a prismatic vision. But in reality, what really happens is that becomes the source. So it's like saying which came first, the chicken or the egg, or the seed or the tree. So one leads to the other. It's basically a cyclic system that you have, and that recycling is very important, and to understand death in that particular scenario is very critical. Only then we will understand potential energy and potential as well. And it's for the same reason that I'm moving away from calling HRD or human resources development or human resources HR as human potential, because there's so much more meaning to the word potential than as a resource. If it's a resource, you're trying to utilize it and seeing what maximum you can get out of it from a human being. But when you're talking of potential, it is immense, in fact infinite, and how you get and tap that infinite potential and keep moving forward in your evolution, not stop at just being human, is the whole idea behind it. So potential energy as well as death energy are very critical and very profound subjects, nothing to be looked down upon or looked with a negative aspect.
Okay, but okay, shall I ask? Okay, thing is, when we subtract the kinetic energy from the potential energy, when the origin itself is potential energy, there will be a negative connotation. That is it not?
No, it's a question of how much of the potential energy you are able to extract out. So that's the reason why this difference comes in. See, most people are always wondering why Lagrangian is defined as kinetic energy minus potential energy. Always we've been talking about conservation of energy, which means the total energy is the potential energy plus the kinetic energy. Why shouldn't that be maximized or minimized? No, this is the difference, because that is what you're able to utilize. There is a latent quantity which is the potential energy. How much of it are you extracting into kinetic energy is what this difference is all about, and that's what comes into play in life, comes into play in a mechanical system, in an aircraft, how fast it flies, how much further it can fly, the range. All of these aspects depend upon this particular difference, and that's the reason why the stationary principle, and again the stationary principle even in mechanics, not only in Ananda maximizing as I talked about, but even in mechanics, there are very beautiful examples. We'll probably cover it in one of the future talks, where we look at it's not always minimization of this Lagrangian, sometimes maximization. That's why it's very wrong to call it a principle of least action. It is the principle of stationary action, or the principle of stationary Lagrangian. That's what it really is. And that's why you have a huge evolution in the history of the variational principle itself.
Yeah, maybe sort of dynamic equilibrium.
Right, absolutely. Everything is in dynamic equilibrium, and that's the dance of Nataraja Shiva.
Yeah, thank you, sir. Thank you.
You're most welcome, Hari. Thank you.
Sir, I think Guru has another.
Yes, please, Guru. Most welcome.
Yeah, you can share your thoughts on entropy and irreversibility of events coupled with chaos as in mechanics and life.
Absolutely, yeah. Very interesting. So the applicability of the variational principles and the special structure which arises out of them slowly starts diminishing as you bring in these aspects of irreversibility and non-equilibrium situations. So as I said, thermodynamics is something that comes out of the macro structure, averaging out the quantities in the microstructure, and that is only equilibrium thermodynamics. When you go to non-equilibrium thermodynamics, again you have an issue. Irreversible processes, again you have an issue. But that's where, again, as I said, modeling is something which is not exact but approximate, which means that you tend to go as close as possible to the reality, and that's where weak formulations come into picture. So you don't have an actual variational principle, but you have something very close to a variational principle, so that you're trying to get towards that structure. And entropy maximization is again a very, very, very critical thing, and that's where you actually see this loop being completed, going from the microstructures, variational principle which is governing it, which is a fundamental law of nature, to the macrostructure where you're averaging out, you're talking of statistical mechanics or statistical physics over there, and with that statistical physics you're trying to reach to equilibrium thermodynamics, and there you're seeing the role of entropy playing it, and it completes the entire circle.
Thank you. Thanks a lot once again.
Pleasure, Guru.
I think Vignesh has a question.
Please, Vignesh.
He says that I think VAM's potential in other disciplines is not explored as it can be applied to any energy functional. And your thoughts on that?
Absolutely, yeah. So it's something that we are sitting on a huge landmine and we don't know what to do with it. We are just utilizing it for very, very simplistic problems, which of course are of profound implications, but there are many, many more problems that it can be applied to. In thermodynamics, for example, in fluid mechanics, in fact, Berdichevsky himself has applied it to problems as complicated as turbulence. And therefore, variational asymptotic method is something which can, with appropriate tweakings, work with even irreversible processes that Guru mentioned. And therefore, Vignesh, yes, we have a huge potential that is lying dormant, not only within us human beings, but within this application of the variational asymptotic method as well. And that's why we need so many more people working on that. Depending upon the problem that they want to apply it to, we can definitely look at how we can take it forward applying the variational asymptotic method. Thank you very much, Vignesh.
The thermodynamics aspect, I saw it in one Berdichevsky's paper. He had applied to it to thermodynamics and to irreversible process. He was discussing in one paper. I think we had it once in May. I remember.
Absolutely, yeah.
It's potential in other fields.
Yeah, it's the whole idea is to get to the bigger picture, because unfortunately the way Western science has progressed is in compartmentalization. Whether you take medicine where you have specializations for all the way from orthopedics to neonatology to geriatrics, etc., and you start treating certain parts of the body different from each other and from the mind. Same way it has happened with respect to the aeroplane, for example, whereas birds and insects both get their propulsion as well as the aerodynamic force of lift from the same source, that is the flapping of the wings. We tended to separate that out. The Wright brothers had a separate system for the engines and separate system for the lift, which is the wing. Now, the same thing holds in this case as well, that we have compartmentalized thermodynamics and mechanics. They are things that completely relate to each other. And it's not only these two, the many other branches of mechanics, because of the interaction of the fields that are involved. Yes, some interactions are strong, some interactions are weak, and therefore we focus on the stronger interactions to get practically relevant solutions for certain specific applications. But if you're looking at it from the idea of development of knowledge, development of wisdom in a much more fundamental perspective, then you have no choice but to look at these in a much more holistic fashion, like Ayurveda does as opposed to allopathy.
The point here is about interaction potential. For example, in gravitational, when studying to gravitational bodies, we do have something called the gravitational potential. So, in order to study many bodies which attract each other in gravity. There is, one has to define a gravitational potential between these bodies. So these many body potentials exist in gravity, as well as when you take the micromechanics using atoms and interaction between atoms, you require a many body potential, intratomic potential between atoms as well. And these are all dependent on the energy functional. These are all dependent on the energy functional and the lattice structure. And hence the variational asymptotic method will be transferred to, I think many people have overlooked or not looked into VAM at all as a mathematical, just a mathematical method. Thank you, sir. Thank you. I think you are right.
It's a pleasure, Vignesh, and you summarized it very well, because that is one of the key takeaways from this whole discussion that we are having.
Okay, so I mean, Professor is here. Probably we can take another 10 minutes of his time.
Absolutely.
So we don't keep,
you're most welcome.
Then if there are some questions, I think this is a nice time to ask them, I guess.
Yeah, this is what discussion is all about. It's no one-way traffic. We need information transfer both ways. Concurrent multi-scale modeling.
Right. If nobody asks questions, then I will start asking and I'll eat up all the 10 minutes.
I have a question. Ajay,
yeah, please go ahead. Somebody had a question.
yeah, I just want to know, like, machine learning can be enabler for composites analysis and design.
Absolutely, Ramesh, because see, the whole idea of the evolutionary process, if you look at our genetic system, it's something that contains the genes, characteristics right from the plant to the animal, even including the reptiles, etc. So it's something that you have learned over time, and that's what karma is all about. You're basically learning, and that's machine learning. You're basically learning from the situations that you have come out of, and that's where history and the past helps you into creating your responses for the future in a better way. So no longer are you reacting to situations, you're only responding to situations, knowing that you have an infinite ability to respond to those situations. And the background for that is the machine learning. So machine learning is something that is going to be very, very critical in the case of composites, even in healthy structures, but even more so in the case of damaged structures, where you try to learn about the mechanics of the damage involved, be it the fiber breakage, the fiber matrix debonding, or the delaminations, or a matrix cracking, or combinations of these, and how they affect the response of the system, and how you can learn from that to predict in a completely different scenario that you don't have as part of your data for the machine learning, and how you translate that data to understand future. So that predictability is something that we have enormous potential now, especially because of the huge big data capabilities that we have now to take forward machine learning for the analysis and design of composites, especially related to their failure.
Thank you, Professor. I have one more question.
Yes, please go ahead, Ramesh.
Can we think of a Navier-Stokes equation as a supreme equation for fluid flow? And also, can variational asymptotic method applied to solve this with a dimensionally reduced models?
Excellent question. Yeah, see, the Navier-Stokes equation is something that is, it's kind of established as the pinnacle of fluid mechanics over a long period of time. Now, this is basically a differential equation. So this is like a differential approach, like what we are doing with Newtonian mechanics, for example, but it is using an Eulerian field instead of a Lagrangian field. Now, the whole idea of a variational asymptotic method, or for that matter any variational principle, is to have a functional and then try to minimize that and to get the data from that. And in many cases, the variational principle can be used to do an analysis of the system without even deriving the governing equations and solving them. So we need to go to the functional, which is prior to the Navier-Stokes equation, or put the Navier-Stokes equation, which is basically a differential form, to an integral form, and that's where we can start applying these. And again, because of the involvement of shear over there and the boundary layers, etc., there are certain irreversible processes which are involved, and therefore you may not have an exact variational principle over there. You might have to go for an approximate variational principle, which can then be governed by the asymptotics. That's where, as opposed to a regular variational principle, variational asymptotic method works much more brilliantly, because with these approximations you can take into account the small parameters involved, not only with the geometry but with the physics of the problem, in terms of how these shear stresses of the fluid on a particular structure or between their own layers, how big or small these are compared to the pressure forces, for example, the pressure that is involved, for example, and all of these can create new physical small parameters which can help the variational asymptotic method apply very beautifully, albeit in an approximate way, when especially when you have highly shearing flows. But as I said, in the case of turbulence, for example, you already have works of Berdichevsky which have been published. So there's absolutely no reason why we can explore how these things can be applied to fluid mechanics problems in a much bigger way, because most of the applications, or almost 95 to 99% of the applications, has been with respect to solids, except for a few of Berdichevsky's works. So but the potential is enormous. So as Vignesh was pointing out, there's applications with thermodynamics as well. So there's absolutely no limit here, because now we are not talking of laws. Laws are things that have much more limited validity. When you're talking of a principle, there's something that you're trying to achieve without any kind of conflict or constraint in the sense of the methodology. There are constraints or conflicts in terms of the problem definition, but not in terms of the approach that you take. And that's where the variational asymptotic methods application to all these problems will happen in the coming centuries in a much bigger way, because it's a principle. It's basically a guiding factor which says that this is how nature works. This is the least effort principle, and we have to identify what are the small parameters governing there, so that we can sort out and see in this whole crowd of parameters, crowd of variables, especially the dependent variables, which of them are really important for a particular application. And that has to be done not just by our emotions or our just our training for in the past, that this is important, I think, or that is important, I think, that is important, he said, and therefore I'm taking. No, let mathematics decide that. Let the physics decide that. And that's where the variational asymptotic method is so powerful, in letting science and math do the work in determining what is important, what is not important, and therefore coming up with a set of governing equations much more easy to solve than the original problem. And that's where Navier-Stokes equation needs to go as well.
Thanks, Professor.
Pleasure.
Is action an appropriate functional for arriving at the Navier-Stokes equation? This is Vivek here, sir.
Vivek, can you repeat that? I didn't hear the first part of your question.
So can action be taken as an appropriate functional to arrive at the Navier-Stokes equation? It's an intuition that comes to my mind.
Yeah. See, there's a lot of work which has been done on this. And when you talk about action, you typically are talking of the original form that it was introduced in by Maupertuis, as I mentioned, as the product of the mass, velocity and the distance, where it takes into account in an indirect way just the kinetic energy. But many other aspects of the energy might be involved. So if you generalize it action functional in that particular way, like for example how Hamilton did it, then yes. So that's one of the ways which has worked wonders not only in solid mechanics but in fluid mechanics as well. But it has not been studied in a very detailed manner. So yes, using that action functional in a much more generalized sense, you can probably deal with Navier-Stokes equation. But at this stage, of course, we are speculating because we're not actually done it. The proof of the pudding is in actually eating it. But I, from my long experience with it, do not see any obstacles in doing that. Just that it's not a trivial thing to do. It requires a completely dedicated research to accomplish that. But it's something which definitely is accomplishable.
Sir, can I continue one more question?
Yeah, please go ahead, Vivek.
I would just like to understand, like what analogy would fit into the action as a functional? Like we've been trying to find analogies to other things.
Yeah.
What analogy would you propose for action? Because it's something like, as you told, it's a funny thing being put in.
Yeah. Actually,
I'm also on the same boat.
Right. Because when he first introduced it as just mass into velocity, yes, we can understand momentum. Mass into velocity into distance traveled. Come on, give me a break. That's what most people, that's how they reacted to him at that point of time. But it's very interesting because if you take velocity as ds by dt, if we talk as m into v into s, where m is the mass, v is the velocity and s is the distance. So then v becomes ds by dt. Now if you do that, then you can show that this same thing can actually become with a factor of 2 the kinetic energy in an integral fashion, because at that time of Maupertuis they were still working on scalar quantities which are not in an integral formulation. It looked very funny, but the same MVS can actually be shown to be nothing but kinetic energy. So it becomes in a very special case of what we know today as the Lagrangian or the Hamiltonian, because in the situation where the potential energy is 0, you have just the kinetic energy, and that integration of the kinetic energy over time becomes something that you're trying to minimize over there, and therefore the action potential has a particular way of approaching that. The other beauty of that is the integral from T0 to T1, where these two times can be quite arbitrary, and therefore a lot of information which you may not have may not be necessary to solve the problem. So that's the beauty of using this particular action functional, but we can't use it in its very rudimentary form as it was introduced, but by generalizing it depending upon the specific application.
Sure, sir. Thank you.
Pleasure, Vivek.
Can I ask a question? Professor, this is Sudeep.
Yes, Sudeep.
Yeah, thank you very much for your nice presentation and a very, very deep and insightful presentation. And I have one question regarding one point. Can we link the effect of generation of nonlinear noise? I mean, noise are mostly, in reality, we find it in having the characteristics of nonlinearity in noise in the system. And that can it be linked with in the light of Hamiltonian's mechanics? As you said, that Hamiltonian's mechanics it has different viewpoints. So can it be explained? Can it be linked?
Very, very good question, Dr. Day. See, this is basically very interesting because, see, once again, acoustics is something associated with the acoustic energy, and again there are vibrations which are basically involved, and mechanical systems also vibrations are basically involved. So if you're talking of noise from that perspective of an energy that is associated with that particular noise, then there are ways to do that. Unfortunately, I'm not an expert on that because I've not worked on acoustics, but the very fact that energy is involved in that process and how you can take that energy into account is what is important. I can say that from the analogy of friction. So, for example, friction is a way that you're basically losing out on your overall energy because that's making the process irreversible. Noise is something very similar. You're losing out on that particular energy, be it vibration. Again, you're losing out on that particular energy. How do you tap into those parts of the energy and bring them into the variational formulation would be a very, very interesting thing. Again, this is an open question because I've not done that. But once again, I would say, just like to a previous question, that this is something which is feasible but non-trivial. So this again, you will not have an exact solution, but you will have approximate solutions which are practically implementable for many problems of analysis and design of actual structures where noise is very critical. For example, in the case of helicopters, where you're looking at cabin noise, how it is getting affected by the noise generated from the rotor, for example, how you isolate that, the ARIS systems and things like that. In designing some of these, much better decisions can be made once you understand this from a variational perspective, because a lot of the trial and error method will go away and you'll have much well-informed decisions onto how to redesign the RS system, for example, in order to reduce the cabin noise coming from the main rotors.
So just to follow up on that.
Yes.
So I mean, are there any interesting papers on acoustics
Ajay, yeah.
and friction where, so Ajay here, sir.
Yeah.
So are there any interesting papers from VAM where it has been applied to friction and acoustics? That would be very interesting to see, because like you said, friction, I mean, from other side of things, people think about it as a dissipative process. But again, like, even though your friction energy is lost, it is converted into something else, like it goes into heating up something. So energy is not just like dissipating away, really. Only thing is people just make that dissipative assumption because it's easy to work with. So you don't have to worry about how it is getting heated and all these stuff like that, right? I mean, so are there anything interesting there from VAM which could be a reference to look at? And
very preliminary work that you did with Jaikiran, for example, can lead to that, Ajay. You mentored Jaikiran, one of our master students in a couple of years back, where you looked at contact mechanics from a bolt perspective, but from a friction perspective, in terms of the dissipative mechanisms involved, I don't think, at least from what I have seen so far, there is any specific paper on applying VAM to such dissipative processes involving friction. But basically it's kind of a non-trivial, again, extrapolation of the contact mechanics, that problem that you are working with Jaikiran for.
Right. Okay. Yeah, so that's why I was very interested in it, because the contact mechanics is another.
Yeah, I have not done a very rigorous search on that particular area of the literature, but it might be that some literature has escaped my attention. But as far as I know, that's probably the only work where we try to use VAM in the contact mechanics scenario. We need to do a more rigorous search to see if there's something else as well.
So also about acoustics, in like, especially since you're working on helicopters and Professor Hodges has been working for a long time on it, was there any opportunity to explore like acoustics, or any of his students, and has anybody explored acoustics? Because that's a very interesting area with helicopters. I think noise reduction is a very interesting topic, and to look at that.
Absolutely. So acoustics, of course, is given a lot of importance, but nothing that I know of in terms of application of VAM for that. Professor Hodges himself has done a little bit of work on related to acoustics, but it's before he got introduced to VAM by Professor Bernoulli. So these are times before that. As you very rightly pointed out, it's a very major problem in the case of helicopters in particular, but in many other vehicular structures and mechanical structures, especially involving motion. And so mechanics and acoustics are very, very intricately related to each other, and applying VAM to that is something I'd love to explore in the future.
Thank you, Professor. Yeah. So these are like kind of open areas where there's lots that
can be done. It's good that we are having this discussion, because it's throwing open so many potential applications for VAM, which I think many of us can take forward in the form of collaborations.
So just another question, like I mean, I would, if somebody else has a question, please bring it up. Otherwise, I will eat up all the time. Like you said, there are a lot of models that are there where people just tweak something, add a parameter in there, and keep publishing, and they get published in quite good journals, right? I mean, let me not name anybody in here, right? And everybody knows about this. And so, I mean, so what are the interesting areas of composites where there's let's say, a lot of potential for work in a way? I mean, I'm just kind of for like some of the younger researchers here who are here. I mean, these are the papers that they will look into when they go into any big journal and have a look at it. Most people will go by numbers. For example, anybody who wants to grow in their career, they look at how many papers you have, what's the impact factor of this journal, rather than the quality of the work per se sometimes.
Right.
So in a way, kind of, what is this, let's say, like you said, the state of the art in composite modeling. So what do we know, and what is the open areas that are there where young researchers can look into and explore?
Very, very, very good question, especially from the perspective of takeaways, especially for students attending this. I think in terms of what needs to be done, typically I think nature is the best inspirer. What it has already achieved and what we haven't yet in engineering, and how we could probably mimic that. The whole idea is making the structure more and more efficient. That's the very bottom line of going to composites from metals and other typical structural materials that we used to use earlier, which means that we have to take that forward. How to take that forward? Again, nature shows us that multifunctional composites is one very, very critical area, where you try to build in not only the ability to handle loads, but also to do some other work. For example, energy storage, it could be energy transformation or energy tapping, actuation, sensing, which is what a smart structure is all about, and many other, like electromagnetic functionality in terms of antennas being primary structures as well. So many such possibilities are there, where again the interaction of multiple fields come into picture, and in the interaction of multiple fields, Newtonian mechanics fails miserably. So you need to have variational principles in general and variational asymptotic method in particular in order to handle such problems. The other thing is in terms of getting to more high fidelity models of what already exists without having to do too much of number crunching. So again, analytical solutions which give a lot of feel into the problem in terms of understanding the physics is something that has been overlooked over a long period of time. So looking at that in terms of seeing how much can you reduce the numerical crunching and just still get the relevant useful information. And then when you want to use the numerical number crunching, again, not do it from a very blind perspective of using all the data that you have. You have tremendous resources in terms of data, but not all of that might be useful. So extracting out which of the data is useful, which is not useful, and trying to put that to best use is something that we need to do with the modeling of composites as well. And then in terms of increasing the efficiency further and further of the numerical processes, adapting methodologies from other fields, like for example, Ramesh pointed out machine learning, artificial intelligence, things like that, things that are developing in the other fields. We need to borrow, just like how I showcased a very simple example of how variational principles first started from optics and then landed up in mechanics, where now far more work is done in variational principles of mechanics than in our variational principles of optics today. But the source was that in optics. My professor D. Hodges, he used to attend what are these brown bag lunches, where we carry our own lunch in a brown bag and listen to talks in completely different fields from what we ever heard. And in many of those always lead to looking at things from a different perspective, because we've been looking at our problems of research that we've been working on for so long that we tend to become like a horse that we are seeing in one particular direction. We are forced to see just in that, and some other field, somebody else might be doing it in a much more efficient way, and that with a little bit of tweaking can be applied to our own problem. And that's, I think, the key in being open to the methodologies which are being applied in other fields. So the methodology plays a very critical role, and that's where I think the question of how is very important. It's not just a question of what you want to do and why you want to do it, but how you do it, because that's the how is what builds up the efficiency into the process and also the accuracy, and both of these together you have a win-win combo.
Thank you very much, Professor. That's a wonderful.
And the other aspects of composites that you're asking, a lot of work has been done primarily for polymer matrix composites, but there's a lot more room for metal matrix composites, ceramic matrix composites, carbon-carbon composites. I think a lot of things need to be done, because for high temperature applications, especially in aircraft engines or in space applications, etc., these become very critical. And though a lot of experimental work has happened there, analytical work and even numerical work, still there's a lot of room for further improvement over there, because now you're talking of thermomechanical fields and also maybe some other fields, electromagnetic fields and other things, and how these systems respond in such a situation is something that we need to understand much better. And once you bring in metal matrix composites, for example, you're no longer talking of only elasticity. That's fine as long as small strains are fine. When you have larger strains, you end up in the plastic regime as well. So how you bring in plasticity into this whole ball game. These are all things with respect to composites that you have to look at. Other thing is polymers are very, very eco-unfriendly, which means that a lot of people are looking at natural composites, especially for secondary structures. And natural composites, most people so far had been looking at natural fibers only. But you need to have a natural matrix as well. And that's an area again where people have started already working. And therefore, that's something that new researchers in composites really need to up the ante in terms of getting to that as quickly as possible, and trying to, if not come to the levels that man-made composites are capable of today, at least try for most of the secondary structures how we can use very, very effective natural composites, natural in the truest sense, both from the fiber and the matrix points of view.
Sir, Siddharth here. I do have a question. Hello?
Okay, go ahead, Siddharth.
Sir, can you hear me, sir?
Yes, Siddharth, I can hear you.
Sir, me being associated with you for some time, so I have seen what sort of work has been happening in VAM. Sir, but I do have a question. What will be the limitations when we are applying VAM to problems like high velocity impact, and problems like involving cutting of machining of polymer matrix composites? When we are trying to apply VAM for these sort of processes, what would be the limitations and challenges?
Yeah, excellent question, because it's again practically very relevant, both high impact problems as well as machining of composites, because these involve loads which change much more with time. So what we are typically talking of, whether it's an impact problem or the machining problem, is instead of statics that we commonly deal with or dynamics in a general loading situation, we are talking of very high frequency problems. And very high frequency, again, in an inverse sense, results in certain other small parameters that you can take advantage of. And Kahnschau Ley in Germany, in Bochum, University of Bochum, has done a lot of work related to these high frequency problems, not specifically related to machining of composites or the impact mechanics problems, but a lot of takeaways from those high frequency problems using the variational asymptotic method are things that we can take away for applying it to impact mechanics. As you might know, we already did a big project with GTRE for the impact mechanics involved with an aircraft engine. In the case of a blade out situation, the containment structure is required to take the impact of the blade in such a way that the blade doesn't exit out of the containment or out of the engine housing and hit the wing or something else, but it has to be within that. And now those impact mechanics problems we try to deal with using VAM, and yes, it is not trivial, but once again we were able to look at to the extent to which we can use variational asymptotic method there in terms of understanding the micromechanics of the problem. See, the whole idea is always to proceed in that way. Have the smaller building blocks, and those smaller building blocks always are amenable to variational principles, and then once you apply the variational principles there in the micromechanics of a containment structure, for example, then how you translate that into understanding the macromechanics of the containment structure as a whole. that information transferred through a concurrent model is basically where this fits in. So variational asymptotic method may not be applicable for the entire problem as a whole, but in the building blocks of the problem, which enable the impact mechanics problem to be analyzed much more efficiently. Same is the case with the let's say a drilling of a composite or any other machining processes that you might have, where you can try to do it in a much more efficient way, where the loss of strength and stiffness of the structure which is machined, the material which is machined, is much lesser.
Thank you, sir. It was really a good explanation, and I never had gone through all these processes. Yeah, thank you so much.
It's my sheer inspiration, Siddharth. Thanks for the question.
Probably we can have one last question maybe, and we have already taken a lot of time.
I think Shrikant had a question.
Okay.
Some more questions are available in the chat window. Dr. Rajneesh is having, and other people also
Okay.
having. Can you take Ajay?
Are there? Okay, sorry, I didn't see that.
Audible, sir?
Yes, who's this? Rajneesh? Yes, Rajneesh. Yeah, please tell me, Rajneesh.
Good morning. Thank you.
Very good morning.
Wonderful talk. A quick one. I mean, which you were explaining very well on the applications. So, two applications which come to my mind, which I believe earlier the lab has worked on, is also on the MFC for the energy harvesting. The second one from the engine domain, on the jet engine, which I got in the Rolls Royce. So that is more on the looking forward on the housings and some special self-healing type of structures, which Composites is definitely the best candidate. So these two applications can be one of the, again, good candidates for applications of VAM. Just to complement which you just mentioned, the Ajay's question. So quick question is, I mean, that is more on a tangential note, but in line
Rajneesh, I'm getting a lot of noise at your end, or is it from somewhere else? I don't know. If everybody else can mute their microphones, and Rajneesh, if you can speak closer to the microphone. I could hear the gist of what you said, but missed quite a few words in between.
is it better now?
Yeah, kind of, yeah. Yeah, please go ahead, Rajneesh.
Right, sir. So, I mean, I was just mentioning briefly about the key application that you were addressing earlier to Dr. Ajay. That one is the MFC, where the lab, I remember the word, one of the words, and also the self-sealing composite structures, where VAM can or potentially it might be already work going on. I remember in Delft, I mean, people working on that quite aggressively. So, on the themes which you really picked up, so I have one thought. So the thought is on learning from the butterfly effect and the chaos theory in conjunction with nonlinear dynamics, and how to work with and handle the initial conditions for the optimization of what I now call, thanks to your inspiring from your talk, the functional of life. Yeah.
Absolutely. Brilliant question that, Rajneesh. I just forgot some of the words that you used.
I said like butterfly effect and the
Yes,
chaos theory.
yeah. The butterfly effect and the chaos theory is really good that you brought that up, because this actually relates in a very intricate way with what Professor Guru Prasad was pointing out earlier as well, in terms of the entropy. So in terms of understanding the chaos theory and the butterfly effect, and bringing in a holistic perception in terms of the interaction of multiple fields, some of them strong, some of them weak, I think that's the real key in improving the methodologies. So entropy will play a very, very critical role in understanding that. And since we already have a methodology by which we can go from micromechanics using the statistical mechanics or statistical physics principles to equilibrium thermodynamics, and then bring in the chaos theory in a non-equilibrium situation along with the butterfly effect, then we'll be able to relate multiple things to each other, both in the engineered systems as well as in human life as well. Many of these principles, like for example the Gibbs free energy, etc., play a very, very critical role in this. You mentioned MFC, etc., where you have multiple fields which are involved, and therefore you're talking of free energy from a thermodynamic perspective, and that will give a lot more insight into mechanics for engineered systems as well as for human life.
Right, sir. And that's what now I think I'm getting inspired to work on one small article which I'll be titling as Functional of Life.
Mm-hmm.
That would be like really good.
Excellent. Really
Thanks
look forward to that. Yeah.
I really thank Ajay and NTU, and thank you.
Thanks, Rajesh. Ajay, I think your microphone is muted.
Oh, sorry. I think it could be good to stop the session for now here, and we will say we are not stopping it. We will say to be continued, right? So I think there's a lot of enthusiasm for everybody. When I'm here, waiting to learn a lot more. And you have stopped at a very critical juncture, like a TV serial, where we don't know what is going to happen in the next season.
Yeah, but unlike a TV serial, this one moves so slowly that you can skip a few episodes in between and still catch up. So hopefully I'll make it so interesting when we have future talks as well, so that nobody misses it and brings in their friends as well.
So I wouldn't mean like a Hollywood.
No, I was just kidding.
10 episode season rather than the Hindi serial where you're like 36.
Absolutely.
So,
and what really makes it engrossing, Jay, is apart from the initiative that you have taken, the very proactive participation from our group in terms of asking the questions. More than my own talk, I actually enjoyed myself personally in answering these questions.
Thank you, Professor, for joining in. And before people leave, I just want to let them know that next week we will be having Professor Guru Prasad from IIT Bombay. He'll be talking about micromechanics and homogenization, and it's a variation asymptotic method where he'll be exploring another angle of it. Professor Guru Prasad was also a student of Professor Harursampath. I think most of you would know about it when he was at IISc. So please don't stop coming in. Please join in. You can go to the website, themechanicsdiscussions.com. So all the upcoming lectures are already there, and the links are already there. So please join in next week as well. I would like to thank Professor Harursampath for joining today, and I think we should have another session or like several more sessions, I would say, to understand all of these, and I think there's a lot of enthusiasm. I am definitely interested in. Only thing is Professor Harursampath has to make time to join in there, and whenever he has time, I think we'll try to get him here and talk to us in a way. And thank you everybody for joining in. A lot of questions, like he said, it is very important that people join in and kind of ask questions. Otherwise, it's not very nice if there's a one-way talk, and then I start asking questions to the professor and he's talking to me. We have an individual. I could probably call up on WhatsApp and have a talk. So, but then when more people participate, then it kind of makes it nice. Also, kind of brings in a lot of perspectives, I think. So I would put the website address in the chat, the mechanicsdiscussion.com. So please go in there. You can just subscribe there. I'm not going to send you a lot of emails because sending you emails means I need to do the work. So I will probably send in. Sorry, I think the link is wrong. The mechanicsdiscussion.com. So yeah, I think right. So there'll be probably there's a link to subscribe there. You can have a look at it and just add in your name and email. You will not get a lot of emails. It will just be once a week. For August, we are planning 4 lectures. For September to December, it's probably going to be 2 a month because I think everybody will have classes and so on and get busy with work. So if you subscribe just 1 week before or a few days before the lecture, I will send out an email to let you know that this lecture is coming up. So that way you can kind of be updated with what's happening in there. There's a lot of interesting talk we are trying to bring in. After Professor Guru Prasad, I think there's a talk on machine learning by Rajneesh. He was here for a few minutes ago. He was asking questions. And he'll be talking about machine learning and how we use these things in Rolls-Royce to kind of do a lot of things in there. Then we'll be having some lectures about flapping wings. So slightly moving from solid mechanics to fluid mechanics regime. And I think this would be a very interesting discussion where they did some CFD with bringing in chaos and solving the Navier-Stokes. I think there were some questions related to that. So they're kind of like trying to bring in a lot of interesting talks in here. Please do join in every week, and hopefully we'll have these numbers and it will be nice to interact with all of you. If you have any questions, you can always send in an email. You can just go and leave a note, and I will be more than happy to write to you immediately. Thank you very much.
Thank you very much, Ajay. It's an excellent initiative, as I said right in the beginning, and the kind of variety you're building up into the repertoire is really amazing. I would also like to advertise for Guru Prasad and Rajneesh's talks in the next two talks. These are two fabulous human beings, apart from being great researchers and a lot of experience related to mechanics, giving completely different perspectives. So I think you would enjoy it as much as you enjoyed my talk, if not better. So I really would welcome all of the participants here to join in for Guru's talk as well as Rajneesh's talks in the coming weeks.
Thank you very much, Professor. Everybody have a nice weekend, and see you next week.
Thank you very much, everybody.
Okay,
Bye-bye.
Bye.
Thank you very much.
Thank you.